Have you ever seen a deck of cards? There are 52 cards in total, each with different suits and values, and it's small enough to fit in a pocket when you go traveling. However, what if I told you that the deck of cards you can find anywhere is technically greater than the entire world we live in? That's crazy, right? But you see, there are 1.33 times 10 to the power of 50 atoms on Earth. Taking out the nerd stuff, that's a number that looks like this. These are the atoms that make you, that make your mom, that make your dad, that make the tree in your backyard. Every single one of those are made upon billions of atoms. And yet, assuming you properly shuffle a deck of cards, there are 8 times 10 to the power of 7 ways to shuffle that, which looks like this. And that number is 620 quadrillion times more than every apple, plant, loved one, and bad education channel on this planet. How did we find this number? Well, that's what you're here to find out, because in this short episode, we will systematically prove with the power of fundamental counting principles why a deck of cards no diffs the entire world. So, what are fundamental counting principles anyway? Well, fundamental counting principles, or FCP, is a rule used to find out the total number of outcomes in a given scenario. It's divided into two phases. The first phase is meant to pick out the amount of individual choices in a scenario, then put them in the boxes over there. Then the second phase multiplies those boxes together to find all the possibilities in that scenario. To make that more digestible, let's use an example. Jimmy here has a date, and like all reasonable individuals do, he wants to pick out his outfit of the day by picking at random because he likes gambling. He only has 3 different shirts and 4 different pants because he owes the rest of his money to the casino. So, how many different possible outfits could he wear? Let's first split this into our phases, shall we? We can see over here that Jimmy has two individual choices to make an outfit. First, he has to choose which one of his shirts he would like to wear, and the second, he has to choose which one of his pants he would like to wear. And we can already see the number over here, so let's put that down in our phases. First, we know that he has 4 sets of pants, so let's put that down as 4. Wait, it's lagging. 4. And second, we can see that he has 3 shirts. So let's put that down as 3. Okay, now we have to move on to phase 2, which is multiplying these numbers. However, before we do that, I would like to explain further why we need to multiply through the use of this cool graph. Now, this graph looks like the roots of the tree, but instead of giving nutrients to the tree, it's giving nutrients to your brains. Okay, aside from all the puns, this is meant to show how you make choices. First, it shows the first choice that Jimmy would have to make. He has to choose which one of the pants he would like to wear. So he has to choose either gray, cream, blue, or dark blue. The thing is, there are there are smaller roots for each of those big roots because he also has to choose his shirt so that he can make an outfit. He has to either choose blue, yellow, or dark green. Now, the thing that this root shows is even if you wear the same pants, you can still have a different outfit depending on which of the shirts you use. If you wear gray pants but you wear a blue shirt, it's different from if you wear gray pants and a dark green shirt. Because of this, both of them are considered different outfits, so all of them need to be considered. This is why you need to multiply, because you're not only considering which one of the pants he's trying to wear, you also have to consider which one of the shirts he's gonna wear with those pants. So, let's do that in our phases again, shall we? Back to phases, we have 4 pants times 3 shirts, and that is equal to 12. So let's put that in problem 1. 12. And actually, if you check back on our root system, you'll notice that we have 12 different small roots. This is because it shows us all of the different possibilities for all of these things, and because this is 12, that means our answer is correct. Jimmy indeed has 12 different outfits that he can get from his outfit gambling. That was a lot, so to help you get your head around it all, Let's try this in a problem with more choices to see if you get it. So back to phases, let's go to problem 2. Timmy's frozen yogurt shop offers a choice of 5 flavors of yogurt, 4 different types of syrup, and 8 different toppings. So how many possible combinations of frozen yogurt can customers order? Once again, we will break this down into 2 phases. For phase 1, you can see that there are now 3 individual choices somebody can make. First, they will have to choose which kind of yogurt they would like. Second, they have to choose which kind of syrup they would like. And third, they have to choose which kind of toppings. Because of this, we will have to use all 3 boxes now and fill them up with the corresponding numbers. So 5 different types of yogurt, so we put 5 here on the first box. 4 different types of syrup, so we put 4 over here in the second box. And 8 different toppings, so we put 8 over here. Now, because of the root system earlier, we know that we have to multiply these. So let's put these in these other boxes and multiply them. Skipping past all of the multiplication, you guys can pause the video here and do it on yourself, but skipping past that, we know that 5 times 4 times 8 is equal to 160. So let's go here to problem 2 and write here 160. Wait. I think my thing is lagging, so I'll just do it here. 160. Okay. Now, I'm not going to do the root system for this because 160 little roots is a long thing and is pretty tedious. But if you guys have the time, I would encourage you to try and make the root system so you can see all 160 of those little roots and understand better how all of this leads up. But I think that's it for the second problem. Okay, assuming because we're done with the second problem and assuming all of you guys get all of it naman, friendly reminder, you guys can always go back to the start of the video to restart the problems and see if you get it. But assuming all of that's done, it's time for the most awaited part of this video, because I'm sure you're all wondering how we got that number for cards at the start, and that's what we're going to show you here. Okay, so the first thing that goes into the cards problem is thinking about what shuffling cards means. Shuffling cards, if you shuffle it perfectly, like correctly, every single card has an equal chance of being at the bottom or at the top. It's all random, right? I'm just gonna write that down here. Because of this, we know that the last card, the bottom card over here, there are 52 options that can be the bottom card. It's 52 because there are 52 cards in the deck, and because we know it's random, every single card has an equal chance of being at the bottom of the deck. So there are 52 options. Next, for the card on top of it, just imagine this as a card. The card on top of it has 51 options. The reason this is, it isn't 52, it's 51, is because the card at the bottom can't be chosen twice. Let's say the card at the bottom is the 2 of diamonds, right? It's very bad diamonds. The card on top cannot be the 2 of diamonds again. It can be any other card aside from the 2 of diamonds. That's why instead of 51, instead of 52, it's 51. Okay, let's erase that, shall we? Okay, after that, we have to consider the card on top of that, which is going to be 50 because of the same thing we said earlier. And then the card on top of that will be 49, and so on and so forth. But you kind of get the idea why it's such a crazy number now. Because if we were to go from top to bottom, first we would to do all of the phases, we would need a total of 52 boxes. Because it's just that much, and they would be 52, 51, 50. I can't write them all. I do not have enough space here, but you get the idea, right? This, and so on and so forth, which leads to the crazy number that you saw at the start, because that's the true power of combinatorics. Just in case you didn't know, that's what we're studying now. Combinatorics, the engine behind percentages. And because of that, technically, That is why cards are literally a quadrillion times better than our entire world. So, that's pretty cool, but I think that's the end of the video, unfortunately. So, here are some practice problems to improve your skills. These are based on problems 1 and 2. These take a little bit more creativity, like what we did with the cards, so feel free to take more time with this one, especially if you find these problems easy. I'll give you guys 5 seconds to take a picture of both of these. 1, 2, 3. Don't worry, by the way, the problems will be in the description. But that's it for me. See you guys next time, and I hope you guys enjoyed this episode.